Hello and welcome to Unit 3. In Unit 3 we're going to learn about kinematics, the study of motion. And to begin Unit 3 we're going to look at one-dimensional kinematics. Before we simplify down to one dimension, we're going to start by writing the first two of the constant acceleration equations in their full vector form. The full vector form says that the position r equals the initial position plus the initial velocity multiplied by time plus 1/2 times the acceleration times time squared. Okay. This is the first of the constant acceleration equations. The second is found by taking the derivative of this. So dr dt gives us the velocity, and that is going to equal the derivative of r naught, which is 0, the derivative of v naught t, which is v naught, and the derivative of the 1/2 at squared term becomes the acceleration multiplied by time. Now really quick, let me take a moment and just write down what all these variables are really quick. So r is the position. For whatever time you're at, it's the position. I can even write it as it's the position at some time t. R naught is the position at time equals 0. V is the velocity at some arbitrary time t, whereas V naught is the velocity at t equals 0 seconds. Acceleration is A. Good spell. There we go. And T is time. Okay. Now, remembering that positions can be found or written as the location of an object in three-dimensional space. So that'd be xi hat plus yj hat plus zk hat. And similarly, I can do the same with velocities. It would be an x component in the I hat direction plus a y component in the j hat direction plus a z component of the velocity in the k hat direction. Now, assuming that we can separate our motions, so nothing in the x direction depends on the y or z direction. The same thing for y not depending on x or z not depending on x or y. That allows us to simplify our equations. And for now, we're going to simplify down to one dimension. In one dimension, either x or y, these equations simplify to be x equals x naught plus v naught xt plus 1/2 a sub x t squared. And vx is v naught x plus a sub xt. Okay. Before I go too much further, I want to point out that if you had started with the definition of acceleration being a change in velocity divided by time and integrated this, you would have landed at the second equation, or integrate again and you get the first equation. Since we are not really integrating yet in this class, I did not start this process there. Okay. Sometimes you may want your direction to be x, sometimes you might want your direction to be y, in which case just take all the x's and change them out for y's. It works the same. When we think of the constant acceleration equations, there's typically one more equation that also comes into play. And that equation is a combination of the two equations already written down. what you need to do is take the second equation and solve for t. Okay. Then plug it into the first equation. That results in this equation. Oops. Well, it will if I can write it correct. Vx squared equals v naught x squared plus 2a sub x times x minus x naught. Okay. And again, you can just change out the x's for y's if you want to work in the other dimension. Lastly, there is one additional equation that sometimes is included in the constant acceleration equations. This last one, I very, very, very rarely use, but it is occasionally needed, so I'm going to include it for completeness sakes. This equation relates the average velocity to the velocity at time t plus the initial velocity divided by 2. And these four equations, 1, 2, 3, 4, are the constant acceleration equations in one dimension. And I should really put my subscripts on down here. Okay. I now want to think about what do these equations result in if we think about this motion graphically. Okay. We're going to start with our easiest option, constant position. If position is constant, somehow I landed on constant velocity there. If position is constant, then x is going to be a constant value. And if we think about v being dx dt, this is going to be 0. And if we think about acceleration being dv dt, this will also be 0. We can get that same result from the constant acceleration equations. Namely, if we look at this one, okay, if position is constant, then x will equal x naught. There's no velocity, so v naught x is 0, a sub x is 0. And now we can graph these. I'm going to use one vertical axis to try to keep everything together. My horizontal axis is time in all three cases. This first one will be position, the middle one will be velocity, and the bottom one will be acceleration. So the position is constant. Might be positive, might be negative, but regardless, it's the same value everywhere. Velocity is constant, or velocity is constant and also 0, and acceleration is 0 as well. So this is a sample of the three graphs we would get for constant position. Next, I want to think about constant velocity. If velocity is constant, and we think about the middle, or the second of the constant acceleration equations, if velocity is constant, that means that the acceleration is 0. This term goes away. And if we then think about the position equation, the acceleration term there goes away as well. As before, graphing, putting position on the upper graph, velocity in the middle, acceleration on the bottom, and time on the x-axis in all three cases. Our acceleration graph is 0, so that's just a straight line right here on 0. Our velocity graph is constant. In this case, let's let it be a negative number, whatever it happens to be. There it is. Okay. Our position graph takes a little bit more effort to look at, but if you look at it closely, you'll realize this is the equation for the line. On the y-axis is our position, X naught is the y-intercept. V naught x, or in this case just v because it is a constant velocity, is the slope, and t is on the x-axis. So notice the two equations both have x's in them, but they're not serving the same purpose. So we have y equals mx plus b. This is a line, and the slope of that line is the velocity. Since our velocity in this case is negative, then our graph has to have a negative slope. There we go. This value up here is x naught, and this is v naught x, if you will. Okay. Lastly, if we think about constant acceleration, then I have to think about both equations in all their glory with all of their terms. Okay, as we have in the last two slides, position, velocity, acceleration, time on the x-axis in all three cases. And in this case, we have acceleration constant. Let's let that constant acceleration be a positive value. Okay. If we look at the middle equation, I'm sorry, I always refer to this as the middle one because I write them with the x equals x naught equation on the top, the vx equals v naught x equation in the middle, and the vx squared equals v naught x squared equation on the bottom. Okay, so if we look at the velocity equation, if you will, we are again dealing with a line. The y-axis is vx, v naught x is our y-intercept, a sub x is the slope, and t is t. Yes, t is t. T is on the x-axis. So we again have a line. The slope of that line is the acceleration. So since our acceleration is positive, our velocity graph has to have a positive slope. This value right here is the initial velocity. Okay. And that brings us to the position graph. The position graph is a parabola. Okay. I'm going to need that point above. Here I see that my velocity is negative, which means my initial position has to have my position graph has to have a negative slope in this area. Just remember, dx dt is the velocity. Since the velocity is negative, dx dt has to be negative, which means we have to have a negative slope. At this point where the velocity goes to 0, the slope has to go to 0, so it becomes the bottom of a bowl, if you will. And then it's going to come back upward, something like this. Okay. This spot right here, I've drawn it at 0, but in general, that is your initial position. And so the graph of position versus time is a parabola. Okay. Now I've created a file to help with this process. Okay. I will post it to Brightspace. It'll be up there for you. In this file, I have cells here for the initial position, the initial velocity, and the acceleration. I then calculate, using the constant accelerations, what the position, velocity, and acceleration are as functions of time, and then I graph them. So for example, in the last example, we had a positive acceleration. So positive 3 we can see, and there it is sitting at positive 3. Our initial velocity is negative 6, and the velocity does have a positive slope. And we see that our position graph does look like a bowl with an initial position of 1. I'm going to encourage you to use this Excel file to practice this. Okay. So for example, if I were to give you the equation x equals 5 minus, we'll do meters, 5 minus 3 meters per second t minus 5 meters per second squared t squared, and v equals negative 3 meters per second minus 10 meters per second squared t, could you graph them? Okay. Well, comparing these, comparing the equations to the formulas, we see that our initial velocity is negative 3 meters per second. We see our acceleration is 10, and up here, remember, this value is 1/2 the acceleration, so those two values are consistent. Here's v naught again at negative 3, and our initial position of 5, so this would be x naught. So now I can make my graphs. X, v, and a, all as functions of time. So our acceleration is negative 10. That's going to put it down here, and I can label that axis as negative 10. I should put units on this. I'll just put them to this side here. Meters per second squared, meters per second, meters, and over here this is in seconds. Okay. Our initial velocity is negative 3, so that is going to put this here. And the slope of this graph has to be negative, which means it's going to go down, and it's going to keep going down, but I don't want it to cross the acceleration graph, so I'm going to let it go. And remember, the slope of this line should equal negative 10 meters per second squared, because the acceleration is the derivative of the velocity. And lastly, what does the position graph look like? Okay. Well, again, it's going to be a parabola. It's going to start at x equals 5 meters. I also see that my velocity graph is negative and always stays negative. Therefore, the graph of x versus t has to have a negative slope. So it's a portion of a parabola. I don't know if I'm at the top here. Most likely I am not. So I'm just going to kind of bring it down like this, keeping in mind that this might not be the top of the parabola. I can now go over to my Excel file, put in those values. 5, negative 3, and negative 10. And I see that indeed I have part of a parabola for position. Velocity is a straight line with a negative slope, and acceleration is constant at negative 10. I can also work these problems the other way and start with the graphs and bring out the equations. So the first thing I'm going to notice is the acceleration is 6. The initial velocity is at negative 5, and the initial position is 0. Knowing those values, I can plug into the equations. So the initial position is 0. The initial velocity was negative 5. And the acceleration is 6. And I forgot the square here. I also have my velocity equation. The initial velocity is negative 5 again, and the acceleration is 6. I can also think about more complicated motion. Okay. So here I have a graph of position versus time, and I want to create the graph of velocity versus time that would correspond to this. Anywhere where I am a local maximum or local minimum, that's a point where velocity is going to go to 0. So here and here in the motion, velocity has to cross the x-axis. In this region, I see that the slope is positive, therefore I'm going to have a positive velocity. In this region, the slope is negative, therefore my velocity is going to go negative. And then after the next 0, it turns and goes up positive. The general shape of this will be correct. Obviously, there's no numbers, so we don't need to check that bit of it. If we were being really, really careful about this, we would verify that where the slope is bigger on the position graph results in bigger velocities. But again, the general shape is more or less correct. We can also do the exact same process going from velocity to acceleration, because acceleration is found from the derivative of the velocity. In this region, the velocity is more or less flat. That means the acceleration is going to be 0 for most of that region. Same thing on the other end. We got to go to 0 on this end as well. And then in between, my slope is negative. Therefore, my velocity has to, or my acceleration has to go negative. So something like that. Now, it probably should be a smoother curve, but again, general shape is correct. This concludes this part of Unit 3.